everyone. In this lecture, we will introduce the fundamentals of graph-based SLAM. When we work with autonomous vehicles or mobile robots, one of the most important challenges is performing mapping and localization at the same time. Today, we will explore how to represent the SLAM problem as a graph, how to optimize it, and why this approach is powerful in real robotic systems. Now, let's begin our journey into the world of graph-based SLAM. This course has been developed collaboratively with significant contributions from many researchers. Among them are Hongri Zhang, Matthew O'Kelly, Johannes Betts, and many others who played important roles in shaping this educational material. Thanks to their collective effort, you are able to learn SLAM through this well-designed content. We are grateful for the opportunity to learn from one another. Unless otherwise noted, this work is distributed under the Creative Commons BY-NC-SA 4.0 license. This means the material can be used freely as long as attribution is given, it is not used for commercial purposes, and any sharing is done under the same license. First, I introduce the fundamental problem setting behind SLAM. On the left, we have localization. Here, we assume the map is already given, and the robot uses sensor data to estimate its current position and orientation within that map. In the middle, we have mapping. In this case, the robot's pose at each moment is known, and the system uses sensor measurements to gradually build a map of the environment. On the right is the core challenge we truly want to solve: SLAM. Starting with no prior map, the robot must use sensor data to build a map while simultaneously estimating its own trajectory within that map. In other words, localization and mapping must be done at the same time, making this a highly challenging problem. The conceptual breakthrough in SLAM came from realizing that when mapping and localization are formulated as a single estimation problem, the system actually converges. Even more interesting is the fact that landmark correlations, something many early researchers tried to minimize, are actually the critical component of the solution. The stronger the correlations become, the better the overall estimation. The simultaneous localization and mapping, SLAM. Problem asks if it is possible for a mobile robot to be placed at an unknown location in an unknown environment, and for the robot to incrementally build a consistent map of this environment, while simultaneously determining its location within this map. The conceptual breakthrough came with the realization that the combined mapping and localization problem, once formulated as a single estimation problem, was actually convergent. Most importantly, it was recognized that the correlations between landmarks that most researchers had tried to minimize were actually the critical part of the problem, and that, on the contrary, the more these correlations grew, the better the solution. This slide explains dead reckoning, one of the most basic methods for estimating the position of a moving robot. Dead reckoning calculates the current pose based on a previously known pose and the robot's measured motion. In our F110 platform, the VSC reads the motor's ERPM and converts it into longitudinal velocity. The servo angle provides the current steering direction. By feeding these values into a simple kinematic model, we can estimate how far the robot has moved and how much it has rotated. This process is what we call odometry. However, one major drawback is drift. Small errors accumulate over time, causing the estimated pose to gradually diverge from the true pose. This is why we need SLAM or additional sensors to correct these errors. Imagine placing the car in a completely unknown environment. At this moment, the car has no idea what surrounds it. It doesn't know where the walls are, nor the location of any obstacles. Nothing at all. This is where the SLAM problem begins. One of the car's key sensing tools is the LiDAR. It emits laser beams in many directions and measures how long it takes for each beam to return. From these return times, the system computes distances to the surrounding surfaces. It's not a full map yet, but it is the first glimpse the robot gets into the structure of the world. When the LiDAR measurements are converted into coordinates, they form a collection of scattered points, just like what you see here. These points represent portions of the walls and obstacles within the robot's field of view. It's still incomplete and fragmented, but as SLAM progresses, these pieces accumulate and align to form a consistent map. Now let's try to build a map using what we have. We know how the cars moved from odometry, and we have distance measurements from the LiDAR. By combining these two sources, we can begin to construct the shape of the environment. Let's imagine an ideal world. If our odometry were perfectly accurate, and if every LiDAR measurement were exact, we could simply take each scan and place it in the correct location according to the robot's movement. By translating and rotating these perfect measurements, the scans would align beautifully, forming a clean map. With perfect odometry, every movement of the robot gives us an exact new pose. At this moment, no new scan has been added yet, only the robot's updated position. When we collect a LiDAR scan at this new pose, it aligns perfectly with the previous scans. By rotating and translating the scan according to the robot's pose, the map grows cleanly and consistently. As the robot continues moving, perfect odometry gives us an accurate trajectory. Each new pose becomes another opportunity to place the next scan in exactly the right spot. As scans accumulate at each pose, they align flawlessly, forming a complete and perfectly consistent map. Under the assumption of zero error, SLAM becomes nothing more than stacking each scan in the right place. The robot moves through the environment, accumulating LiDAR scans at each pose. With perfect odometry, every scan is placed exactly where it belongs, producing an accurate trail of measurements along the robot's path. After some time, the accumulated scans begin to reveal the shape of the environment as a sparse point cloud. It's not a full map yet, but the outlines of walls and obstacles gradually become recognizable. In this example, the measurements look sparse, but if the robot continues driving and collecting more scans, the points become denser and converge into a realistic representation of the environment. Under perfect odometry and perfect sensing, SLAM essentially reduces to stacking more and more scans until the map becomes complete. In the real world, odometry is far from perfect. Wheel slip, motor RPM errors, and small control inaccuracies accumulate over time, causing the robot's estimated pose to drift away from the true pose. LiDAR scans are also noisy, with small errors in each range measurement. As a result, the perfect map-building approach breaks down once uncertainty enters the system. The LiDAR scans themselves are mostly correct, but once odometry begins to drift, even correct measurements get placed in the wrong location. So the sensor data is right, but the mapping algorithm puts it in the wrong place because the pose estimate is wrong. As the robot moves, odometry errors accumulate further. Rotations tend to introduce even larger drift, causing the estimated pose to deviate noticeably from the true motion. If we keep stacking scans under this drift, the points begin to scatter in places that don't match the real structure. In the end, scans accumulated on top of incorrect odometry produce a map that no longer resembles the real environment. Points drift away from walls, straight structures become warped, and obstacles lose consistency. This is exactly why SLAM is challenging in the real world. Even with correct measurements, placing them at the wrong poses destroys the map. Here, the robot believes it is slightly ahead of its true position. Because the odometry has accumulated error, the LiDAR beams are projected into the wrong places. The measurements themselves are mostly correct, but the projection frame is wrong, so every point is misplaced. This is the moment the map begins to drift away from reality. As the robot keeps moving, the error accumulates further. Each LiDAR measurement is still mostly fine, but because the robot's estimated pose is wrong, all points are projected incorrectly. Walls that are straight in the real world begin to appear stretched or curved in the map. The distortion grows over time. When orientation errors occur, the distortion becomes even worse. If the robot mistakenly believes it has rotated more than it really has, the LiDAR points fan out in the wrong direction. Any small existing error grows dramatically. If the robot keeps mapping while believing the wrong pose, all new points lose their meaning. The rectangular room we expect can no longer be reconstructed. Point clouds accumulate in incorrect regions, destroying the structure of the environment. In the end, even after completing a loop, the result is no longer something we can call a map. The walls and the circular obstacle become unrecognizable. When odometry drift combines with sensor projection errors, the entire map collapses like this. And this is exactly why SLAM is necessary. As we continue driving, the errors in odometry keep accumulating, and the noisy LiDAR measurements are placed in the wrong positions. Eventually, the map we generate no longer resembles the real world at all. Everything drifts, the walls bend, the circular obstacle becomes distorted, and the entire map looks completely different from the ground truth. At this point, it becomes clear that simple mapping based on raw odometry and LiDAR is not enough. This is exactly why we need SLAM, a method that simultaneously estimates the robot's position and builds a consistent map of the environment. There are generally two major approaches to solving SLAM. From our earlier example, we observed that the biggest issue comes from the compounding error in state estimation. When we relied only on odometry, the error gradually accumulated and eventually distorted the entire map. The first approach is filtering-based SLAM. Methods such as the extended Kalman filter or particle filters attempt to improve state estimation and provide better transformations of the sensor measurements. However, filtering alone cannot recover the true position of the robot, and small errors continue to accumulate over time. This becomes a major limitation when mapping large environments or when the dead reckoning estimate drifts so far that filtering can no longer pull it back. The second approach is graph-based SLAM. This method stores robot poses and sensor measurements as nodes in a pose graph and uses relative pose estimates as constraints with associated confidence. A scan matcher is used to find correspondences between nodes. Then all constraints are optimized simultaneously to adjust the entire graph. As a result, the system corrects local estimation errors through global consistency. Today, the industry has largely shifted to graph-based SLAM. With modern solvers and optimization techniques, the computational burden is no longer prohibitive, and this method can handle large-scale environments while maintaining high accuracy. Next, we will take a closer look at how pose graph optimization works. One of the most important ideas in a pose graph is the relative relationship between poses called edge constraints. In this visualization, the red car and the gray car represent two consecutive pose estimates of the robot. The red pose shows where the robot believes it is, while the gray pose represents another possible estimate influenced by odometry drift or sensor noise. The red and gray lines represent correspondence between feature points observed in LiDAR scans. These correspondences define how the poses should relate to one another, and they become the constraints in the pose graph. Now we can imagine each constraint as a spring. The spring tries to pull the two poses toward the relative position and orientation defined by the measurements. It behaves like a spring in both translation and rotation, making the concept intuitive. Imagine the edge constraints as a spring, and it could be stiff or soft, both in translation and rotation. Since this is created from odometry, the more confident you are in your odometry measurement, this spring will be more stiff, more resistant to change. And if you're less confident in your odometry measurement, this spring will be softer and easier to move around. The stiffness of this spring depends on how much confidence we have in the odometry. If the odometry is reliable, the spring becomes stiff and strongly resists changes. If the odometry is uncertain, the spring becomes softer and allows the poses to move more freely. As illustrated, the gray pose shifts by different amounts depending on the stiffness of the constraint. Imagine the edge constraints as a spring, and it could be stiff or soft both in translation and rotation. Since this is created from odometry, the more confident you are in your odometry measurement, this spring will be more stiff, more resistant to change. And if you're less confident in your odometry measurement, this spring will be softer and easier to move around. In a pose graph, every edge constraint acts like a spring connecting two robot poses. This spring represents how strongly those two poses should maintain their relative position and orientation. The spring has two independent stiffness components, one for translation and one for rotation. In other words, we can control how much the spring resists stretching in position and how much it resists twisting in orientation. The stiffness of this spring is determined by how confident we are in our odometry. If the odometry measurement is highly reliable, the spring becomes very stiff. It strongly resists any attempt to move the two poses apart from the position predicted by odometry. Even small deviations will generate a strong corrective force. On the other hand, if we are not very confident in the odometry, the spring becomes soft. It allows the poses to shift more freely and bend into a configuration that better matches the rest of the constraints in the graph. This spring-based interpretation explains why graph-based SLAM works so well. Confident measurements exert strong influence, while uncertain measurements remain flexible. Together, they guide the system toward a globally consistent and well-aligned pose estimate. In essence, edge constraints define how tightly or loosely each pair of poses should be connected, allowing the pose graph to settle into the most coherent structure. These spring-like constraints exist between many pairs of poses throughout the pose graph. During optimization, all of these springs are adjusted simultaneously so that the total tension is minimized. As a result, the poses settle into the most consistent configuration possible, leading to an accurate final map. In slide 53, you can see the poses moving into alignment as the constraints pull them into their corrected positions. Does this look familiar? This is exactly the same scan matching problem we saw earlier. In the picture, multiple LiDAR scans from different poses are stacked without proper alignment. The key idea is that all of these mismatches become edges in a pose graph, represented as tension between nodes. Later, during optimization, these tensions determine how the poses should move to satisfy the constraints we define. Now, let's run our real-world example again. This time, as we drive, we will also construct a pose graph. We now repeat the same real-world experiment, but this time we will construct a pose graph while driving. A pose graph is a structure in which each robot pose becomes a node, and the relative motion between poses becomes an edge. In other words, we record every place the robot has been, and we connect these places using the odometry-based relative transformations. Looking at the illustration, each time the robot moves slightly to the left, a new car icon appears on the screen. Each of these icons is a node in the pose graph, representing one estimated pose and its corresponding LiDAR scan. Between each pair of consecutive poses, the relative motion computed from odometry is added as an edge. So at each step, first, we insert the LiDAR measurement into the node, and second, we add the odometry-based relative pose as an edge. This gradually builds up a full graph of the robot's trajectory. If you look at the right side of the figure, you will see a chain of gray and blue car icons accumulating as the robot moves. Those icons are the nodes, and the conceptual links between them represent the edge constraints. So in summary, nodes contain the estimated pose and its scan. Edges represent the relative pose constraints obtained from odometry, and as the robot continues moving, the pose graph grows naturally, exactly as shown in the illustration. On the right side, you can see multiple car icons. These represent pose guesses the robot has made. But notice that the actual ground truth and these guesses start to differ. This mismatch will grow if we don't correct it. As we continue moving and adding nodes, errors from odometry accumulate. The robot thinks it's going in a straight line, but actually it's drifting. This is called pose drift. The red scan lines now start to mismatch the real wall. This is why odometry alone is not enough for localization. As we continue, the map becomes increasingly distorted. LiDAR keeps observing the correct environment. But because the odometry is wrong, the map pulls apart and bends in unnatural ways. We'll have the right measurements from the LiDAR scanner. Mostly, we're going to ignore the noise on scans here. Our mapping algorithm will mistakenly put the points in the wrong position using the wrong odometry. The problem is not the measurements. The problem is the pose from which they are projected. Since the odometry-based pose is incorrect, the correct LiDAR points are placed in the wrong locations. This is why the map begins to look distorted. The measurements are right, but they are being drawn from the wrong pose. As odometry drift increases further, the mismatch between the scans and the real environment becomes more severe. The poses diverge from the true path, and the measurements continue piling up in the wrong places. This slide shows how error accumulates over multiple driving sets. Each race car icon represents the robot's estimated pose after completing a loop. As the robot continues to drive, small errors from odometry and sensor noise start to build up. Initially, the estimated positions are close to the true path. But over time, these errors stack up, and the robot believes it is in a different place than it actually is. You can clearly see that the last poses are significantly off from the starting position, even though the robot returned to the same spot. This is a classic example of drift, and it highlights the need for loop closure to correct the accumulated error. Now let's introduce the important concept of loop closure in SLAM. Over time, as a robot keeps moving and scanning the environment, small errors in localization can accumulate. Even if each individual scan is locally accurate, the global position of the robot may slowly drift over time. Loop closure is the process of recognizing when the robot has come back to a previously visited location. This allows us to create a new constraint that helps pull the current estimated pose back toward where it should be, reducing accumulated error. Let's look at the slide. Here we isolate the blue and red scans. These are from the first and last positions of the robot. Notice that both scans are observing the same part of the map. That means we can connect these two poses with a loop closure constraint. A good way to visualize this is by imagining a virtual spring between the two poses. This spring wants to pull them together because they ideally represent the same location. And since they should overlap, the spring's resting length is 0. This added constraint improves the accuracy of both the map and the robot's trajectory estimate. The stiffness of this virtual spring is determined by how confident we are in the scan alignment. Higher confidence means a stronger pull between the two poses. If our scan matcher is very confident, the spring force will strongly try to pull the two nodes together. This is what we call a loop closure constraint. At the same time, all the other springs between neighboring poses are trying to keep their original shape. Now, the graph is full of tension. It's no longer in equilibrium. Next, we let the graph settle. The system will optimize the pose estimates to reduce the overall tension. Eventually, the graph reaches a new equilibrium. Let's visualize how the graph converges. Now the pose graph has reached equilibrium. The data we've collected now looks much more consistent, and it finally resembles the actual environment. This entire process of detecting revisited places and updating the pose graph accordingly is called loop closure. In technical terms, we treat the graph like a spring network and solve for equilibrium using optimization. Loop closure is what enables graph-based SLAM to work effectively. Because every past pose is updated when loop closure happens, we end up with a more accurate estimate of where the robot was and where it is now. We can further improve our pose estimates by performing additional loop closures. In this slide, notice how we've added another constraint, a new virtual spring, connecting the bottom left and top right of the trajectory. Before this addition, the pose graph was already in equilibrium, meaning no forces were acting on the nodes. But once this new loop closure is added, the system becomes unbalanced. The same optimization process will run again, adjusting the other springs slightly to restore equilibrium. However, not all loop closures are helpful. If we wrongly believe that two observations correspond to the same location and add a false constraint, the optimization will converge to the wrong configuration. In fact, it's usually better to miss a correct loop closure than to include an incorrect one. When doing loop closure, it's crucial to use absolute measurements, like those from LiDAR or vision. Using relative sensors like IMU doesn't help here because it can't confirm if your current pose matches a past one. In this image, we highlight how incorrect matches from relative data can lead to drift. Now that we've refined our trajectory, the next question is, how do we store the environment map? One of the most common methods in 2D is to use an occupancy grid. In this image, we overlay a square grid on top of the scanned points. This is a binary occupancy grid. If any laser scan hits a grid cell, it is marked as occupied, usually colored black. Cells that are never hit remain unmarked. It's simple, but not robust against noisy measurements. Instead of binary decisions, we can store a probability of occupancy for each cell. This is called a probabilistic occupancy grid. Laser hits increase the probability, and misses decrease it. If a cell is mistakenly marked as occupied once, repeated correct scans will gradually correct it. This makes the map more robust to occasional errors. To summarize, this is the overall structure of graph-based SLAM. Sensor data goes into the front end, where a graph is built with poses and constraints. Then, the back-end optimization finds the best configuration of those poses. This loop runs repeatedly to improve both the map and the robot's localization. Real-world SLAM systems also include loop closure detection, error handling, and various heuristics to make it reliable in practice. To wrap up, let's talk about the sensors needed for graph-based SLAM. Interestingly, this approach is sensor agnostic, meaning it doesn't depend on any specific brand or type. It only needs two types of sensors. First, a sensor that measures relative transformations between poses, such as an IMU, wheel encoders, or odometry. These are used to connect the graph nodes. Second, a sensor that measures absolute observations of the environment, for example, LiDARs or cameras. These are used for detecting loop closure. Graph-based SLAM is not only sensor agnostic, it's also agnostic to the scan matching method. You can use any method to match scans: ICP, scan to map, map to map, feature-based, ransack for outlier rejection, and even bundle adjustment. These are all valid choices. However, most SLAM libraries today have gradually converged on using one method in particular: correlative scan matching. Let's begin by introducing the idea of correlative scan matching. Traditional scan matching methods, like ICP or iterative closest point, rely on finding exact correspondences between points in two different scans. They minimize the distance between matched pairs to estimate the transformation. However, this approach is vulnerable to poor initial guesses, and it often gets stuck in local minima. A variant called PLICP improves this by using point-to-line distances instead of point-to-point, which works better in structured environments. But both still require computing correspondences, and that step is sensitive to errors. Correlative scan matching takes a fundamentally different approach. Instead of matching points, it searches over a range of possible transformations to find the best alignment, without needing to compute correspondences. It does this by projecting an entire scan onto a reference map and measuring how well it fits at different positions. You can think of it as sliding the scan across the map and checking where it aligns best. This makes it more robust to noise and bad initial poses and avoids getting trapped in local minima. To make the search efficient, it uses a lookup table that assigns a cost to every possible projection. This way, alignment can be quickly evaluated across many hypotheses. Let's now approach scan matching from a Bayesian point of view. Before, we just tried to find the best alignment using optimization. But now, we want to estimate the probability of the robot's new pose based on what it sensed and how it moved. Let's say the robot starts at pose xi-1, moves with control input u, and observes some sensor data z. We want to estimate how likely it is to be at the new pose xi, given all of this. Using Bayes' rule, we can write this posterior probability as being proportional to two terms. The first is the observation model. This tells us how likely we are to observe ZZ, given we're at pose xi, and using map. The second is the motion model. This is the probability of transitioning from xi-1 to xi, given the control input u. In the equation, this looks like probability of current pose given previous pose, control input, map. And observation is proportional to probability of observation given pose and map times probability of current pose given previous pose and motion. We often model the motion term using a multivariate Gaussian centered around the odometry reading. So the real difficulty is in modeling how the observation matches the map, which is where scan matching comes in. To simplify the observation model in scan matching, we make a key assumption. Each LiDAR scan point is observed independently of the others. This allows us to break down the probability of the full scan into a product of individual point probabilities. Mathematically, this is written as the probability of observation z given pose x and map m equals the product of the probabilities of each scan point zj given the same pose and map. In other words, we're saying, instead of modeling the scan as a whole, we treat each ray independently. For 2D LiDAR, each beam's likelihood depends on which surface the beam would hit on the map. To compute this precisely, we could use ray marching, but it's computationally expensive, so instead we pre-compute the likelihoods using a lookup table. This is what correlative scan matching relies on. It uses a 2D lookup table, where each grid cell stores the log probability of observing a LiDAR return at that position. Now let's take a closer look at how correlative scan matching actually works. First, we generate a cost map, which assigns scores to possible transformations. Think of this as a 2D map where each position reflects how likely a scan aligns at that pose. To handle sensor noise, the LiDAR scan is rendered into this cost map using a blurring kernel. It spreads out each laser point slightly, modeling the uncertainty. Candidate transformations are then generated, typically centered around a prior, like an odometry estimate. Each candidate pose is scored by projecting the scan and looking up values in the cost map. Finally, the covariance of the best solution, how uncertain we are about this match, can also be estimated. This will be useful later when combining multiple scans or for SLAM backend optimization. The left image shows a cost map where bright spots indicate good scan alignment. This image is adapted from Olson's 2009 ICRA paper, a classic reference for correlative methods. This slide summarizes how correlative scan matching selects the best alignment between two scans. We aim to find the optimal transformation denoted as T-star that gives the best alignment. To do this, we consider a range of plausible transformations, different combinations of translation and rotation. For each candidate transformation T, we apply it to every scan point PIP IPI and look up a score based on the likelihood of that transformed point matching the reference map. This is represented by the function L of T times PI. Then, we sum up the scores for all scan points and select the transformation T that gives the highest total score. This is what the equation shows. T star equals argmax over T of the sum of L applied to each transformed point. In simpler terms, we brute force search over many poses and pick the one that makes the scan most likely to be correct based on the map. To speed this up, we can use multi-resolution search. We build a pyramid of lookup tables at different resolutions. The low-resolution ones give quick but coarse estimates, and the high-resolution ones refine the best candidates. To wrap up, let's talk about pose graph optimization. The goal here is to find the best configuration of poses, or nodes, that agrees with all the measurements we've collected. In other words, we're adjusting the nodes to make the observations most likely, based on the constraints between them. To do this efficiently, we use a method called sparse pose adjustment. You can think of it like a spring mass system. Each measurement acts like a spring trying to pull two nodes into the right place. We adjust the whole graph to find the configuration with minimum energy, or in this case, maximum likelihood. Let's begin by understanding how we express the relationship between two robot poses. The function h of Ci and Cj represents the relative transformation between pose I and pose j. In other words, it tells us how pose j should look from the coordinate frame of pose I. This relative relationship includes two main components. First is the rotation component. This describes how much the robot's heading changes when moving from pose I to pose j. It captures the difference between their orientations. Second is the translation component. This describes how pose j is positioned relative to pose I. To express this consistently, we subtract the positions and then rotate the displacement into the coordinate system of pose I. Together, these components form a compact mathematical description of how pose I and pose j are connected in terms of rotation and translation. This constraint becomes one of the building blocks used during pose graph optimization. Next is the concept of the error vector, which plays a central role in sparse pose adjustment. The idea is simple. The error is the difference between two things: what the robot actually measured through sensors, what the current pose estimates predict using the constraint function. The measured value usually comes from scan matching, for example, using LiDAR data. Because sensor measurements contain noise, they may not perfectly match reality. On the other hand, the predicted value is computed from the current pose graph using the function h. The error vector is the difference between these two. A large error means the pose estimates do not agree well with the actual observations. These error vectors appear throughout the graph, and reducing them is the ultimate goal of optimization. In short, EIJ tells us how inconsistent our current pose estimates are with real sensor data. Now we bring all individual errors together into the global objective function, commonly called chi-squared. Each error is not treated equally. Instead, every error vector is weighted according to how reliable its measurement is. This weight is called the information matrix or precision matrix. Highly reliable measurements receive larger weights. Less reliable ones get smaller weights. This ensures that accurate measurements have greater influence during optimization. The total error is formed by summing the weighted squared errors across all constraints. Minimizing this total error is a nonlinear least squares problem. It is typically solved using algorithms such as the Levenberg-Marquardt method. Once this minimization is complete, all poses are adjusted so that the entire pose graph becomes as consistent as possible with the sensor observations. In essence, the system finds the most coherent explanation for the robot's entire trajectory. So far, we've learned how to build a map and estimate the robot's motion within that map. A natural next step is to localize the robot inside a known map. We've already explored this concept earlier using the particle filter. With both mapping and localization available, the next big topic we'll move into is motion planning. This is where the robot not only understands the environment and knows where it is, but also begins to choose how to move through the space in an intelligent and efficient way. This connects all the pieces together: mapping, localization, and finally planning the robot's path. In today's session, we'll also take a look at how to run SLAM Toolbox on your actual cars, so you can apply the SLAM techniques directly on the hardware you're working with.